Good morning, everyone. I am pursuing Mastering Jet Propulsion and Gas Turbine Plant from MS University, Baroda. We present a topic Centrifugal Compressor Stage. This presentation prepared by Megraj Kohil, Jayesh Murjani, and Bhavin Palia. In this presentation, covered topic name slip factor, diffuser, volute casing, stage losses, and performance characteristics. Firstly, we discuss in slip factor. In turbomachinery, the slip factor is a measure of the fluid slip in the impeller of a compressor or a turbine, mostly a centrifugal machine. Fluid slip is the deviation in the angle at which the fluid leaves the impeller from the impeller's blade when angle. Being quite small in axial impeller, inlet and outlet flow in the same direction. Slip is a very important phenomena in radial impellers, and it is useful in determining the accurate estimation of work input or the energy transfer between the impeller and the fluid, rise in pressure, and their velocity triangle at the impeller exit. After we discuss factor accounting for slip factor, like impeller design or geometry, mean blade loading, thickness of blade, finite number of blades, fluid entry condition, working fluids viscosity, effect of boundary layer growth, flow suppression, friction forces on the walls of the flow packages, boundary layer blockage. After mathematical formula for slip factor we discussed, in this the figure shows slip factor denoted by sigma is defined as the ratio of the actual and ideal value of the well velocity component at the exit of the impeller. This is V dash omega 2 divided by V omega 2, where V omega 2 actual well velocity component, V omega 2 ideal well velocity component usually vary from 0 to 1 with an average ranging from 0.8 to 0.9. The slip velocity is given as Vs is equal to V omega 2 minus V dash omega 2 is equal to V dash omega 2 1 minus sigma. The world velocity is given as V dash W2 is equal to sigma V into omega 2. After we discuss Stodola equation, according to Stodola, it is a relative eddy that fills the entire exit section of the impeller passage. For a given flow geometry, the slip factor increases with increase in the number of impeller blades. So account for one of the impeller parameter for the losses. Figure shows. Here his angle is beta 2. Here his circle diameter is 2r. Is sigma is equal to 1 minus pi by z psi into beta 2 divided by 1 minus pi 2 into cot beta 2, where here z is equal to number of blade and pi 2 vr2 divided by u2 for radial tip. Beta 2 is equal to 90 degree, sigma is equal to 1 minus pi by z. And after we discuss Steinitz equation, Steinitz found the slip velocity does not depend upon the blade exit angle and hence gave the following equation. Sigma is equal to 1 minus 1.98 z 1 minus pi by 1 minus 1.98 divided by 0 z into 1 minus pi 2 into cot beta 2, where z is equal to number of blades. Beta 2 varies from 45 degree to 90 degree for radial tip. Beta 2 is equal to 90 degree. Sigma is equal to 1 minus 1.98 divided by z is equal to 1 minus 0.63 into pi by z. After we discuss 1.5 Balaji's formula. An approximate formula given by Balaji for radial tip beta 2 is equal to 900 blade impeller. Sigma is equal to 1 plus 6.2 z into 9 raised to 2 by 3 bracket close minus 1, where z is equal to number of blades, n is equal to impeller tip diameter, I tip diameter. After we discuss diffuser, a diffuser in a centrifugal compressor converts the kinetic energy of the working fluid into static pressure energy by slowing down the fluid velocity. It's located after the impeller and come in various steps. Gas at impeller exit has a high absolute velocity C2 which decreases to a lower velocity C3 in the diffuser. The degree of deceleration and static pressure rise P3 minus P2 depends on the diffuser's efficiency and degree of reaction. As well, we designed diffuser minimize losses P2 minus P3 while maximizing efficiency and recovery of coefficient. Vanless diffuser is lack of veins or blades typically consist of parallel or nearly parallel wall forming a channel. Fluid enters with high velocity and low pressure, exits with lower velocity and higher pressure. Gas diffuser in the van less stress around the impeller before exhausting through the volute casing or directly. Pressure rise occurs due to a diffuse from smaller diameter D2 to larger diameter D3. However, this design often leads to a relatively large diffuser. A drawback of the vanless type is the diffusion is directly proportional to a diameter ratio D3 by D2 and van diffuser. In a centrifugal compressor, the high-speed fluid leaving the impeller enters the van diffuser, where when slow its velocity and increases its pressure through area expansion and diffusion. This conversion of kinetic energy into pressure energy improve overall efficiency. Figure shows first we saw ventless diffuser, after we saw van diffuser. Here show that van diffuser like this vent type this rotor blades in here ventless mean nothing any when are here. After we discuss area ratio, the area ratio in a centrifugal compressor is the ratio of the cross-sectional area of flow inlet and outlet. It's immensely proportional to a compression ratio which relatively inlet and outlet pressure. Highly higher area ratio amplify lower compression ratio and vice versa. When a diffuser with divergent volt can achieve large area ratio for a given diameter ratio. Equations show that the area ratio of a diffuser can be increased by A double dash R is equal to D3 divided by D2 bracket 1 plus bracket d3 by d2 minus 1 bracket close tan theta divided by b2 by d2 bracket close 1 by sine alpha 2 under root ma 1 minus cos square alpha 2 divided by d3 by d2 bracket close raised to square. Increase in the diameter ratio d3 by d2, increase in the width ratio b3 by b2, decrease in leading edge bend angle alpha 2, various combination of a, b and c. Some typical value of this parameter r d3 by d2 is 1.4 to 1.8, ar a3 by a3 is equal to a3 by a2 is equal to 2.5 to 3.0, alpha 2 is equal to 110 to 20 degree. b2 by d2 is equal to 0.025 minus 0.10 range and theta max is equal to 5 degree. In figure shows impeller in a diffuser R2, R3 here B3 and B2. It inlet or outlet. After we graph plotted area, this area ratio AR versus diameter ratio D3 by D2. Here we saw when diverging alpha 2 is 15 degree and theta is equal to 33 degree when parallel alpha 2 is equal to 50 degree and when less diverging theta is equal to 3 degree. After we discuss Mach number at diffuser entry, the Mach number at the entry of the diffuser is measure of air flow velocity relative to the speed of sound in centrifugal compressor. It is initial to control the Mach number to prevent flow separation, shock waves, and other undesirable phenomena that can reduce compressor efficiency and reliability. Operating with a Mach number that is too high can lead to flow choking or shock induction losses, while operating with a Mach number that is too low can result in efficient diffusion and reduce pressure recovery. Therefore, designers carefully consider inlet condition, impeller design, and diffuser geometry to maintain the Mach number within an optimal range for efficient compressor operation. Uh, this is to show in the absence of the endless space between the impeller tip and the diffuser entry. The Mach number at the diffuser entry is given by m2 raised to square is equal to c2 square divided by a2 square. The flow of perfect gas with zero while at the entry is condition below. C2 square is equal to Cr square plus C theta square Cr square theta plus U2 minus Cr2 quad beta 2 raised to C2 square is equal to U2 square pi 2 raised to 2 plus 1 minus pi 2 quad beta 2. After we simplified the equation, we have solving for a given gas and duty fixed value of gamma and delta T is 0 st divided by Tc over. The impeller exit Mach number depends on pi 2 and beta 2. To avoid the possibility of shocks, the Mach number at a diffuser entry must not be greater than zero point 0.9. The actual value of this Mach number will be lower than the given by this equation. Due to diffusion in the endless space, after we discuss volute casing. The volute casing is a spiral space housing surrounding the impeller, like so the spirals have. Its primary function is to collect the high velocity air discharged from the impeller and gradually convert kinetic energy into pressure energy as the airflow through the volute. Its direction change from tangential to radial. The motion is to slow down and increase in pressure. This pressure rise is crucial for achieving the desired compression ratio and delivering the compressed air to the outlet. Here, the endless space before volume decrease the non-uniformities and turbulence of flow entire the volume as well as a noise level different cross section area, rectangle, triangular, or all of this. Free vortex design. Here, the flow through a volume passage is assumed to follow for free vortex flow, which is RC theta is equal to R2, C theta 2 is equal to R3, C theta 3 is equal to K. Ct is equal to K by 3, then alpha is equal to CR by C theta is equal to constant. Q theta is equal to theta by 360 into Q. After we solving here, the volume flow rate Q can be determined from the mass flow rate, assuming the average density of the gas in the volume cassette is equal to rho 4 is equal to P4 RT4. After we discuss construct mean velocity design for obtaining high efficiency, it is found from experience that it's necessary to maintain constant velocity of the fluid in the velocity passage at the design point. This would also give uniform static pressure distribution around the impeller. In actual practice, both the velocity and pressure vary across the cross section of the value passage at the given section. Therefore, to be more precise, the mean velocity and pressure along the volute pressure are assumed to remain constant. For a given value of the mean velocity, the area distribution is obtained from source. The volute radius R4 for a given value of R3 and B3 can be determined. Q theta is equal to Cm into 8 theta is equal to theta divided by 360 into the Q. 8 theta is equal to theta divided by 360 into Q by Cm. For rectangular section, theta is equal to B3 into R4 minus R2. After we discuss volume term in centrifugal compressor and blower, the volume casing logarithm curve ideally start at the impeller exit, but in practice, it's shifted to avoid a sharp edge lip called the tongue or cut water. The size and geometry of this tongue affect performance. Size and geometry of this tongue affect performance. To mitigate issue, the tongue is cut back to a blunt edge, aligning its inclination with streamlines. The tongue location and geometry critically affect outflow from the volute, dividing flow into two streams. Improper tongue inclination lead to soap losses and distributed flow conditions. The gap between impeller and diffuser and adverse circle should be minimized to reduce fluid recirculation and losses. 10 alpha is equal to 10 alpha 3 is equal to dr by r d theta is equal to constant. D theta is equal to 1 by 10 alpha 3 divide is equal to 1 alpha So d theta is equal to 1 by tan alpha into A3 dr divided by r. For a given radius ratio, the angle theta t is radian at which the tongue starts into blood base circle is determined. Theta t is equal to 1 tan alpha 3 in R3 divided by R3. After we discuss stage losses. Stage losses are significant factor to consider when analyzing performance efficiency of centrifugal compressor. First, we discuss friction losses. In a centrifugal compressor occur due to resistance encountered by gas as it moves across internal component like the impeller, casing and diffuser. This resistance generate heat and reduce the pressure rise across the compressor, impacting its efficiency. In impeller entry loss, in a centrifugal compressor, we refer to decrease in pressure and efficiency that occurs as the gas enters the impeller. This loss is primarily due to the conversion of kinetic energy to pressure energy, shock waves formation, and boundary layer effect at the inlet. It's initially to minimize impeller entry losses to optimize compressor and performance clearance losses. In a centrifugal compressor occurs due to the small gap between the impeller and the casing, where some of the compressed gas leak back to the low pressure side. This leakage reduces compressor efficiency. Leakage losses happen when there are small gap or clearance in the compressor's internal component, allowing compressed gas to bypass the intended flow path. This losses decreases the compressor's efficiency and overall performance. After we discuss shock losses, here we saw this. In centrifugal compressor, stage occurs when the airflow experiences suddenly change in the velocity and pressure. So here, the suddenly change, leading in insufficient energy transfer increases turbulence within a compressor. This phenomenon will result in reduced compressor performance and can be lead to efficiency losses and mechanical issues if not properly managed. After we discuss last topic, performance characteristics figures shows here we show figure pressure coefficient versus flow coefficient. Actual performance characteristics plot for our centrifugal stretch. Performance characteristic of a centrifugal compressor or a blower at a given speed can be plotted in terms of the following quantities. PRO is equal to F bracket M dot under T01 divided by P01 bracket close. Pressure coefficient is equal to F into pi. The theoretical performance characteristics of a centrifugal state represent the ideal head or pressure curve, while the actual characteristics consider losses such as a friction shock resulting in variation in performance. Stable operation is limited by surging and choking, with maximum pressure and efficiency usually near the surge point. Unstable flow can occur due to stalling and vent diffusers, but ventless diffuser widens the stable operating range. Local stalling of blades and rotating stall can occur or leading to surging, while choking happens when the max number at the blade or diffuser throat reverse unity. Here show that pressure coefficient and flow coefficient in this side positive, in this side negative. Here shows this is shock losses. Here after friction losses. Thank you.